Hi everyone, today we have Yiannis here with us and he will be talking about his work, Modular Design of Secure Group Messaging Protocols and the Security of MLS. Let's welcome him.
Thanks for being here. I'm not sure, like, you can hear, like, you ready for my microphone?
Yeah, can you guys hear us? Can someone who is watching online, tell us?
Yeah, sure. So I'll present material which basically comes from two papers, like one Crypto 20 and one CCS 21. And it's a joint work with John Alwyn, Sandro Correte, and so first I'll give some context by comparing secure communication protocols with secure messaging protocols. By the way, feel free to interact at any point and ask questions. So in secure communication protocols, like for instance TLS, communication is reliable. It is synchronous and parties are online during sessions, which are typically short-lived, right? So sessions don't last like for years as in messaging protocols. So in communication, in secure communication protocols, resilience and compromise is a minor concern. On the other hand, in secure messaging protocols, communication is unreliable since messages may be lost. It is asynchronous and parties may be offline during sessions. Usually sessions may last for years, like they're long-lived. Think about your applications like WhatsApp and Viber. You have group chats that are there for years, right? So for this reason, state compromise is likely to happen over the lifetime of the session.
So why is it reliable?
Because like some messages, like especially when we have like some properties like forward security, we might drop some keys and some messages might not be delivered. Right? We might not be able to decrypt, basically. So in the two-party setting, we have the success story of the Signal protocol, which is based on the off-the-record protocol. It is used by billions of people, and it's used by apps like Signal, Facebook, WhatsApp, and Skype, Facebook Messenger, and it won the Levin Prize at Real World Crypto. There are many works that study this two-party case, and it's very well understood. So how about secure messaging for groups? The naive approach would be to use a two-party protocol in a pairwise manner. However, this is highly inefficient. It requires complexity and square, so we don't like it. So for groups, we have messaging layer security. MLS started about 3 years ago, and currently we have the 12th version of their draft. And the goal is to standardize a protocol for secure group messaging with log n message complexity, where n is the number of users. There are many contributors in this project, both from academia and industry, as you can see. So in MLS, parties can join and leave the group at any time. They can perform updates to refresh their key material. And they can also send and receive messages. The adversary controls the network and the server. He sees all packets, and he can also modify packets. He controls message delivery, and he can also leak the state of users, right? Yes.
So in the previous slide, you say that party can leave or join at any time.
Mm-hmm.
So do other parties know the identity of like newcomers?
Yes. Yeah. I mean, we will assume a PKI,
Okay.
public infrastructure. So whenever you invite someone, you know his public key base. So here are the main security goals for MLS. First of all, we need privacy. So messages should remain private, should be hidden from the adversary, right? Unless there is a trivial attack. So if we have compromised states, this should be considered as a trivial attack. And we also require authenticity. So messages cannot be changed by the adversary. On top of that, we require two additional properties. The first one is post-compromise security, which basically says that security can recover after state compromise via normal protocol execution. And the second one is forward secrecy, which basically states that privacy should hold even against future state compromise. Right? So if there's a state compromise now, past messages remain secure. This is what forward security means. So the MLS design considers many components, but one of the most important ones is what we call a continuous group key agreement.
So are those images stemming on this server or
malicious server? Yeah.
But we are not trying to hide the communication side of site.
No.
But if
yeah, go.
Why not a malicious server just drop everything? Is that?
Yeah, this is the denial of service, right? It's,
So
he can choose not to forward packets, right? But this is
still okay.
Yeah.
Denial of service.
Yeah, it's denial of service. So the first part, in the first part, I will present continuous group key agreement. So this relates to our first paper. So in our Crypto 20 paper, we define this primitive and we prove security. So in a high level, continuous group key agreement is a primitive which comes with the following operations. One can create groups, add members, remove, update key material. The update operation is the main operation for security. So I will explain later how this works. And also an operation for processing control messages, for processing protocol messages. So in a high level, a continuous group key agreement protocol enables a group of users to asynchronously maintain a shared secret in a dynamically changing group. This is what the primitive does. An execution looks like that. So we consider the execution as proceeding like in epochs. And with each operation, we have a new epoch. Right? With each create, add, remove, update operation, there is a new epoch. So initially, let's say A creates a group. So we're in epoch number 1. And we have group secret I1. And then B is added to the group. This is epoch number 2 with group secret I2. And with each operation, we move on to a new epoch and we have a new group secret. Now, this group secret, is computed and then will be used by a higher layer protocol to do other stuff. In our setting, we do messaging. So this group secret will be used by other users to basically, derive other keys and exchange messages. So the CGKA security model is basically similar to the one we consider for full SGM security, but in our paper, we consider passive adversaries because we are going to add authenticity on top of that. But we're going to add signatures later. So here, we are okay with passive adversaries. And the security guarantees of CGKA are, first of all, privacy, which basically means that the group secret should be indistinguishable from uniform. So in the CGKA security game, as you can imagine, at some point the adversary will challenge the key, and if the security game flips a bit, and if the bit is 0, the adversary receives the group secret. If the bit is 1, the adversary receives a uniformly random string, and he should not be able to distinguish between the two. This is what we require, and also we require the 2 additional properties that we require for MLS. In general, right? So this is one of the basic components that enable secure group messaging. This continuous group key agreement primitive is one of the main components upon which post-compromise security and forward secrecy we rely on.
So this client or the user seems to be on.
Sorry, basically there is no active adversary. The adversary can still leak the state of users, but he cannot inject packets in the network.
So there's no something
like Sybil attack is basically when you have control over the network, right? It's not about it's a different type of attack. Here, the thing is like the adversary can basically do denial of service. He can choose not to forward packets. He can do whatever he wants, but he's not injecting. It's just we have a passive observer. And he can leak state of users. So here is the idea. The adversary executes the game and he's given full access to all operations. And now, let's say he challenges epoch I, the group secret for epoch I. So he's either given, uniform random key or the actual key. So the question is like, is this secret secure? So we define optimal security, which basically means that the group secret should be secure if there is no corruption at epoch I. So the adversary challenges epoch I. If there is a corrupted party at epoch I, then security should trivially break because the adversary knows the state of a user, of a group member at epoch I. However, if there is no corruption, we should be able to prove security for the group secret at epoch I. So if there were corruptions before epoch I, corrupted parties should either be removed from the group or update their state. And also, we don't care about corruptions after epoch I. We shouldn't care. This is what we call optimal security. So I'll now present the TreeKEM protocol, which is the protocol proposed by MLS for CGKA. It was proposed in the MLS mailing list in 2018, and it's based on an earlier work on the synchronous ratcheting trees. And the goal is to have packet size of logarithmic packet size in the number of users. And of course, we have some other works that do actively secure CGKA and also variations of this protocol. So in TreeKEM, the group state is basically a binary tree, and users are the leaves of the tree. So here we have a group with eight users at the leaves, and each node of the tree consists of a public key and secret key for public key encryption. Besides the root. So at the leaves we have the keys of the users that you can get from a PKI, as we said before. So the tree invariant property says that each user knows only the secret keys along the direct path to the root. Okay, so basically, those two parties know SK prime, those two parties know both SK and SK prime, and those four parties, they don't know SK prime and SK, right? They only know elements from secret keys that lie in the direct path to the root.
Question. So for the left mode party, do they know PK prime, SK prime?
This party knows PK prime, SK prime, knows PK, but no SK. It doesn't know SK because this is not in the direct path to the root. So
the public key is known to everyone.
Yeah, the public keys are known to everyone. For this talk, I will consider static groups, meaning that there are no other removes. We have a fixed set of users, right? Because this is enough to actually highlight the securities and insecurities of TreeKEM. So let's see how the update operation works. It's one of the main operations of TreeKEM. So the update operation, let's say party number 1 executes an update. He's basically sampled a seed S0. He's computing PRGs up to the root. So this H is a random generator.
So can you remind me what is the functionality of update?
The functionality is basically for the user to update its state, the key material, so that we achieve post-compromise security and forward secrecy. So this user now, with an update operation, he will update all the secret keys along the direct path to the root.
I mean, in terms of functionality, it just depends the epoch to the.
Exactly. Yeah, and you compute a new group secret. So you basically sample seed for S0, you compute PRG, and you compute the seed for the next level, plus the secret key for that level, SK0. And here we assume that we can derive the public keys from the secret keys. Okay, so we compute the seed for the next level, and we do this up to when we reach the root. And S3 is basically the update secret, the group secret. And in this way, party number 1 refreshes its key material from its leaf to the root. Is that clear? This is a local modification, right? This party, updates its state locally. So how do other group members learn about this modification? The idea is that party number 1 encrypts the seeds under the public keys of what we call the copath nodes. The copath nodes are the circled nodes. Right? We have nodes A, B, and C. So party number 1 encrypts S1 under PKA, encrypts S2 under PKE, and S3 under PKC. And now users below PKC, they know SKC. Right? So they can decrypt and learn S3. Users under B node, they can decrypt using SKB, compute S2, and then compute S3 by applying the PRG operation. So observe that we have log n operations here, right? Yeah.
How does party 1 get S1? Or
Sorry?
how does the party number 1 get S1?
He computes S1 is the output of the PRG.
Oh, but
S1,
S0.
S1, right?
Yeah. But S0 sampled the party 0.
Yeah. It's party 1, so you use party 0, party 1.
Oh, okay, sorry. Yeah.
So this part here, this node corresponds to the party.
Okay.
Right?
Yeah.
So this party owns this secret key SKA.
Okay. How do they know S0? Like they need to know S0.
This party needs to know S1 because he needs to know all the keys from that node to the top, to the root. Right? Because this one is not in the direct path. So this node should not know the key for this, for node number like 1. Okay. And those two parties, they only need to know from S2 to the top. You only know the keys along your direct path. You shouldn't know below the least common ancestor.
Like, how does party 1 know that party 0 wants to update?
How does?
So when party 0 wants to update, how do the other parties know?
Those ciphertexts are being broadcasted to the network.
So EOCMA broadcast channel?
Exactly. I mean, they're being uploaded to the server, and then the server needs to basically send those ciphertexts to the parties.
You say because everything is semi-honest or whatever?
Yes, you cannot modify packets. I mean, the adversary can do stuff in the network. He can split the group basically, but we can still prove security in the presence of group splitting attacks, where he basically sends some packets to half of the group, and some other messages packets to another half of the group. But here's how the update operation works. Do you have any other question? So for forward secrecy, we only keep the keys and we erase seeds. And also, when we consume the secret, the group secret of the root, we need to erase it. Is that okay? However, the adversary observes all the traffic. So he observes, he can collect ciphertext. He collects ciphertext and he can corrupt parties. So let's see like what he can do. Let's see an example which illustrates some issues with TreeKEM's forward secrecy. So here's the tree again. We're in 0 epoch. We have only the users at the leaves. And we are in the initial epoch 0, and I use cross for blank nodes. So initially the tree is blank. So we have an update operation by party number 1. So he computes secrets along the direct path. Then we have an update from party number 3, computes the red path and overrides parts of the keys that were computed in the orange path. An update from party number 5, and finally an update from party number 7. Now the question is whether the update secret for epoch number 4 is secure. And we consider, those, that we call bombs. The bombs are ciphertexts that if you manage to decrypt, you can directly compute the update secret for epoch number 4. So when this party encrypts here, he's basically creating one bomb because he encrypts under the key of this node, right? So there's a bomb here. And also the secret for the upper node is encrypted under the key of this node. So we have another bomb. And similar for the red node. The update secret is encrypted under the secret key of the highest red node, right? So we have 3 bombs. And the question is like, are those the only bombs in the tree? And the answer is no.
Yeah, those bombs using other bombs.
Exactly. So we encrypt, we have older ciphertexts from older epochs. So when party number 5 encrypted this secret under this secret, when he created epoch 3. So if there is a corruption here, the adversary can recover the secret key for this node, and then he can compute all other keys. And of course, it's not only for epoch number 3, but we also have the same for epoch number 2, and also epoch number 1. So you can, via corruption, the adversary can recover keys which enable the recovery of other keys that lead to the root. So basically, for every level I, we have 2 to the I minus 1 active bombs, which basically means that half of the leaves are bombs. And corrupting any user that holds a bomb can break security of epoch secret for epoch 4. So what if users update? So update is the main operation that gives post-compromise security, right? Let's say party number 6 issues an update operation. We have 2 bombs along this path. So by the update operation, those bombs are being diffused. However, we have at most 1 bomb that is being diffused per level. Therefore, still corrupting a party enables recovery of the group secret, and we need at least n/2 updates to diffuse all bombs. So half of the parties need to update, and this is a serious problem, as you imagine, right? Because we said for optimal security, we need 1 update operation. We have the challenge epoch, right? We have 1 update operation for the party who is corrupted, and then we need to have security. So this is a serious issue. And for some parties, if some parties never update, you might never get forward security. So this is very weak. So in our paper, we characterize precisely the level of security that can be achieved by TreeKEM via security predicate. And we use the notion of key graph. And the question is like, whether we can do better or whether we can do optimal. And the answer is yes. So the main idea is that we substitute public key encryption in the protocol with updatable public key encryption. Updatable public key encryption is related to the notion of key updatable public key encryption, which was proposed in Europe in 2018. It is inspired by proposal in the MLS mailing list, and it's basically practical forward secure public key encryption. So let's see how updatable public key encryption works. You know the syntax for standard public key encryption. We have keygen, enc, and dec. And we require correctness and CPA security. So in updatable public key encryption, we have the same list of operations. We have keygen. Keygen now creates the initial keys, PK0, SK0. The encryption operation receives a public key and message and outputs a ciphertext. However, it also updates the public key of the receiver. So from PKI-1, we move on to PKI. And during decryption, the receiver decrypts the ciphertext, recovers the message. This is a type which should be I-1, recovers the message, but also computes a fresh secret key. The secret key is the one that corresponds to the public key. You know, those two operations are synchronized. So whenever I encrypt the public key, I update the public key, and whenever the receiver decrypts, computes the new secret key. And the idea is like we still need correctness, and we also need CPA security. But now the idea is the following: whenever I have a corruption after decryption, the adversary recovers SKI, but it cannot recover SKI-1. Is that clear?
Let me make sure. Where do you use all senders are synchronous? What happens if senders are not synchronous?
The senders, I mean, the senders need to send when you encrypt with respect to a specific public key, right? They need to have the same version of the public key. They need to encrypt with respect to the same version of the public key. The adversary can still split the group, right? But we do care about, we prove security for a specific branch. And for this specific branch that we prove security, you know, we need to assume a specific key, right?
So let's say if the senders are async, then maybe multiple senders will.
The thing is, like, senders, they can send, you know, you can send a message for a specific public key today. I can do it tomorrow. That's fine, right? But we need to, you know, the encryption operation should be with respect to the same public key in order for the receiver to process both.
Okay.
That's the thing. Yeah.
What's the security key of this? Which is what
So the idea is that we first sample PK0, SK0. Then the adversary can basically provide messages for encryption, like and public keys. So we allow here the adversary to provide inputs to the encryption operation with respect to, you know, public key updates. But we want, just before the challenge, to have an honest public key and secret key. Prior randomizations can be, you know, done by adversarial group members, let's say. So I'm a group member, I'm, you know, adversarial. I issue encryptions with respect to public key with my randomness, which is bad. And then I need one good encryption right before the corruption of the party.
So how many players do you just one challenger?
Yeah, it's one challenger in the adversary. But it doesn't have to be like in the context of messaging, this one. It's only, you know, the adversary provides a vector and you compute encryptions and then you decrypt and the key moves forward. And at some point you have the corruption. This single adversary receives a secret key. The last secret key, SKI, and he tries to break security with respect to CI. Sorry, can you repeat that?
You know if there are protocols for this that
the thing is, like, when you start, you know, having this type of interaction, and this is like group splitting kind of attacks, right? Then think about the tree that we described, right? So let's say the adversary creates a fork somehow in the execution, and then you want to prove security in one branch of the execution. And there might be parties that actually exist in both branches, right? So this is very tricky. I mean, you cannot do a lot of things because corruption in another branch might enable you to recover keys on the other branch.
I mean, more narrowly, like if you're updatable.
Yeah. Sorry?
It's like more narrowly to get updatable.
I think this stronger primitive. So your question is about this primitive or in general messaging? It's mostly about yeah, but I'm not sure how would, yeah, we were focusing only on the messaging context, the secret messaging. So this is what we didn't think about it. So let's say we replace now public key encryption with updatable public key encryption. So now observe that under SKC, under node C, party number 1 updates, encrypts S3 under PKC, and after the decryption operation, we move on to SKC prime. So the adversary recovers SKC prime, but he still cannot break security with respect to the previous key. Is that correct? I mean, can you get the idea? We assume corruption after the decryption. So the party decrypts and erases the old key. How much time do I have? Oh, yeah, so skip this one. It shows an execution. So there are many CGKA related works. In our Crypto 20, we define CGKA and prove security against passive adversaries. We have also security against active adversaries. And also post-quantum, I mean, there's a lot of research that happens in CGKA because it is the main component for SGM. The thing is that CGKA enables the computation of the group secret, right? But the final goal is SGM. We need parties to be able to compute, you know, to exchange messages. So we are missing this connection. Before, like our thesis paper, there was no such thing. So I'll move on to SGM now. This is the second part. The MLS syntax, I will go over those ideas quickly. You have operations for initialization of state of users. We have interaction with PKI, you know, for generating signature keys and storing signature keys. We have operations for everything. And we also have a group creation. Now, the idea is that we follow this propose and commit paradigm that is followed by MLS. In MLS, group members send proposals to the network, to other users. And those proposals are like for adding users, removing users, or updating key material, like signature keys. Other users collect proposals and commit to them. So the commit operation in SGM is the one that enables moving to the next epoch. Okay, it's like the update operation that we were discussing on CGKA on the lower layer. So with each commit operation, the user sends a message to the group, which enables them, after processing this message, users move to the next epoch, and also sends welcome messages for new group to new group members. And commit is the main operation for post-compromise and forward security. It's like it will actually call update internally. And we also have operations for send and receive. So here's the security. The security game considers an adversary who basically, again, has access to all operations from group creation, update proposals, commits, and receive, and PKI. He can also leak the state of users by corruptions. He can send bad randomness to users and ask them to compute operation with his own randomness, which is what we call bad randomness attacks. No delete attacks. He can ask users to no delete all keys from their state. And of course, we have injections. Here we go for active security. And also privacy. He can challenge messages. So he can send message M01 to the challenge oracle, and he receives encryption of MB, with for uniformly random bit. And this is for privacy. Now, the technical challenge here is that we need to actually do some form of bookkeeping to understand which attacks are trivial and break security trivial. Otherwise, we can prove security for the corresponding keys for the challenge, not keys, sorry, messages. Now we have messages, user exchange messages. So we need to know which parties were corrupted and whether they got removed, and if the adversary used bad randomness. So we need to do some bookkeeping, and we do this using what we call a history graph. The history graph basically keeps track of the execution data, and we apply predicates, security predicates over the execution to actually, decide whether specific executions have trivial attacks or not. So a history graph is basically a directed tree, right? And we have pointers. So users have pointers to each tree, to each node in the graph. So here we observe that it's like we have a group splitting attack. So, Alice is in B3 and Bob and Charlie are in B2. And with respect to the operations, initially all pointers point to the root. There is no group at this point. One party creates a group. Alice creates a group and she moves on to the next epoch, V1. And then she wants to add Bob and Charlie. So she commits, and then everyone is processing and move to the next epoch. And this is how it works. Some people propose, some users propose something. So proposes an update, another party commits, and this continues. This is how the execution proceeds. And here it's like a removal for Alice. It's being processed and Alice is being removed from the group. Now, history graphs gives us kind of an intuitive way to define predicates over the execution and decide whether whether an execution is legit or not, right? So for instance, here, let's say the adversary corrupts Bob, who is in epoch V1, and then he challenges V2. Here, this is a trivial attack. Why? Because Bob is having all the key material that it needs to process the data and move on to the next epoch. So we need to know whether we have this type of scenario in our execution. And here it's similar thing with respect to, let me check, with respect to group splitting attacks. He corrupts on another branch, Bob, and he's challenging again V2. So here, again, we can have a trivial attack because Bob might still have key material that, you know, affects the execution with respect to epoch V2. However, if before corruption, Bob executes a commit operation, which is basically the operation that refreshes his key material, then we can still prove security for epoch V2. Right? So we need to know if users updated their state or not. So here's the high-level idea. We have a history graph execution, and we have a safety predicate. The safety predicate checks the execution and also receives the safety predicate for CGKA, for the underlying CGKA protocol, together with other predicates, and it says yes or no, basically, whether the execution is legal. And basically, this approach is modular, so you can use different CGKA protocols with different security predicates and actually get security for the new composition. So let's see how the SGM construction works now. I will skip this part. So users continuously agree on secrets. So they execute CGKA and they compute a key. Then this key is given as input to a primitive that we call PRF-PRNG. This is a stateful primitive, and it actually acts as a PRF if the state has high entropy. While if the key that is input to the primitive is a good key, is uniform, it acts as a pseudo-random generator. The output is a key for MAC and a key for encryption, and I will say later. So using the MAC key, we basically mark all messages, all control, or all protocol messages. For instance, all CGK messages are being marked using this key. And then the other key feeds what we call a forward secure group authenticated encryption. And this is basically used in the higher layer for users to exchange messages. This is symmetric encryption. It is a primitive that, you know, considers groups of users, and also provides forward security. So in some sense, we have a group of users, and, you know, we have symmetric keys, and there is a key schedule, and after encrypting to a specific secret key, the key is being erased, and when decrypting with respect to the specific secret key, the key again is erased. So if we have a corruption now, past messages remain secure. And of course, we use signatures on top. So all messages are being signed. So is there any question? So authenticity comes from signatures, the authenticity property of the symmetric encryption scheme, and MACs. Privacy comes from the privacy of encryption, and forward security relies on forward security of CGKA. If you remember, we said that this is a primitive that achieves forward security, and also forward security of group authenticated encryption. Any question? Let's say about post-compromise security now, right? Let's say we have a corrupted party. So when we have a corrupted party, And then users execute CGKA and they derive a fresh group key. Now, from the PRNG security of PRF-PRNG, this is a uniform random key. So we get fresh keys for MAC and FSGAD state. The state is being refreshed and security recovers. There is one important detail here, right? In order for security to recover, we need the adversary to remain passive. We are recovering from compromise now. The protocol is recovering from compromise, which means that the adversary knows the keys, all the keys of at least one part. And this part is updating. Right? So the adversary knows the MAC key, the old MAC key, he knows signature keys, he knows everything. This is why we use MAC together with signatures simultaneously. Because in this way, by updating the CGKA key, and if the adversary remains passive, security can recover. Without, for instance, updating signature keys. Like updating signature keys might be more costly, so then we'll rely on one. Is that okay? But all protocols in this line of research require the adversary to remain passive for one round during the update, in order, after the update, in order for security to recover.
So is everything else like the adversary sector?
Yes, this kind of assumes that the adversary does not have full control of all channels, all users' channels. So the user can find a channel, right? Maybe your Wi-Fi is compromised at home, but at the office, yeah.
Would you have security if they were active, say for some number of updates, and then they stopped being active for a later update?
Yes. Yes. Basically, the idea is that this is a continuous process, right? I mean, the protocol executes, and we want security, we want healing via normal protocol execution. So the protocol might be compromised, for many rounds, but then you have one good update, the adversary is not present, remains passive, and security recovers. This is the main idea. And also, we also cover bad randomness attacks. So imagine that with each commit operation or update operation that I described before, this commit operation can consider bad randomness, which means that this S0 seed that is sampled by the user is being defined by the adversary. So the group secret is basically defined by the adversary. If I define the randomness in this execution, then the group secret is adversarially defined. Do you agree with me? The adversary basically defines S0, and then you have S1 blah, 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 up to the root, which is I, is defined by the adversary. So we can even get security in this setting by using the PRF property of the PRF-PRNG. Because in this case, the key that fits the PRF-PRNG is bad, but we use the PRF security. This is the high-level idea. And again, as you imagine, I said we use predicates for other primitives that we require, we use PRF, PRNGs, and FSGAD. So the SGM security predicate receives inputs for all those predicates and decides whether the attack is trivial or not. Yeah, that's pretty much it. Thank you. Thanks for attending. Do you have other questions?
What do you think are like sort of like the remaining challenges?
Remaining challenges? Maybe we still, UPKE, we use updatable public key encryption here. This, we made this transition from PKE to UPKE. This gives optimal security, but it seems that UPKE is not easy to be adopted by MLS. Because, you know, the operations considered by this primitive are not currently considered by existing implementations of elliptic curve, you know, encryption. So, I mean, maybe finding other ways for, you know, achieving optimal security and relying on standard PKE would be, you know, a nice direction. Yeah. There is a lot of work that happens in the CGKA level. Yeah.
Right. So with the CGKA, we have like TreeKEM. There's also like a typical protocol where you just send a secret to the channel for the user. Because it's like less efficient for sending, but it's more efficient for receiving, right? Just like instead of login. So then what's the motivation and practice of referring to the company?
Like using two channels, you mean?
Or even just like when you send it out, you send it separately to over
You're saying instead of sending all the packets to every user, this is what the question, like doing something better than that?
Or more specifically, like ignoring TreeKEM instead of just like sending the root key to everyone directly over TreeKEM.
Yeah, this is linear complexity. So this is what we try to avoid here.
I guess the argument that you can make is that for receivers, it's cheaper.
Yes. For receivers, it's better, but yes, for actually there is a paper that is doing, you know, they consider CGKA of depth 1, which is basically the idea of encrypting to all other parties. But for the sender, it's very bad. It's linear, and imagine that if you have groups of thousands of people, then it's, you know, it's not easy. Like maybe you don't have the bandwidth, or you know, to do this. Yeah.
Theoretically, maybe this is not the practical, but theoretically, can you get below the
I think there is a lower bound. I mean, this tree-based construction is basically, you know, a folklore thing in general. It's used in cryptography like for years, also, you know, for agreeing on keys. The new idea is like this continuous group key agreement. There is a lower bound, I think, by Yiannis, paper by Yiannis with for concurrent updates. There are also other papers that try to analyze distributions of update operations and try to see whether you can do something better, or like whether you can have concurrent updates. You know, in one epoch, you derive the key via simultaneous update operations. Here we said only one update per user, but you can also have, you know, constructions that in which more than one user update in one. You can basically, it's easier for, you know, the adversary can basically choose to drop some packets, you know, for some guys, right? So with concurrent updates, you're just merging updates and everyone is contributing in a single round.
Okay, let's see if there are any other questions. Let's speak up, maybe. Okay, it looks like we have no other questions.
Okay,
So thank you very much
Yeah,
for the
thanks
talk.
for attending.
And we'll see you